We are surrounded by light and colors in our daily lives. Visible light is but a small portion of the electromagnetic spectrum, which ranges from audio to radio waves in the lower frequencies, and X-ray and gamma radiation in the upper regions. The visible regions of the spectrum range from infrared in the higher wavelengths to ultraviolet in the lower ones. Most of us have seen ultraviolet light from a black light. And what is a black light without a colorful poster to go with it? These posters seem to come alive because the pigments used to create them fluoresce when exposed to ultraviolet radiation. Many minerals fluoresce when exposed to ultraviolet light. This sample of hydrozincite looks like an ordinary rock in normal sunlight, but fluoresces in the green wavelengths with exposure to UV. This sample of calcite does the same, but fluoresces in the red wavelengths. Opals exhibit a very strong fluorescence when exposed to UV light. Interestingly enough, flowering plants also fluoresce when exposed to UV light. The stamens of this Apiaceae flower fluoresce. This Rosaceae flower fluoresces in multiple wavelengths. The pollen in this Lamiaceae flower fluoresces. UV is one of the components of sunlight, so these flowers are fluorescing constantly in daylight. It's possible that the eyes of insects are sensitive to these fluorescent wavelengths, and that the plants are storing fluorescent compound in their flowers and foliage to attract them. Sulfur dioxide is one of the many compounds that fluoresce when exposed to ultraviolet radiation, and we exploit this property of the molecule to measure it. To begin the measurement of SO2, we start with a measurement chamber. This chamber is basically a tube with a gas inlet and outlet, as well as 4 optical ports. We'll need to seal 2 of the ports with windows. The remaining 2 ports are sealed with optical filters. We'll explain the purpose of these shortly. Sample is introduced into one end of the chamber and evacuated from the other end. An ultraviolet lamp provides the light necessary to make the process work. This light is focused into a narrow beam and is directed across the measurement chamber. A 214 nanometer optical filter is used to filter out wavelengths of light that are not useful to this purpose. The UV lamp is pulsed at 25 cycles per second. The purpose of this is twofold. The primary reason is that this minimizes the effects of any ambient light that may be introduced into the process. Secondly, since our resulting signal voltage will be AC, the effects of noise in the electronics is also minimized. An ultraviolet detector is mounted in the measurement chamber opposite the UV lamp. The sole purpose of this detector is to give us an indication that there is enough ultraviolet radiation in the chamber to make the process work. When a sample containing SO2 is introduced into the chamber, the SO2 molecules that are in the UV light path are excited and fluoresce. This fluorescent light passes through a second optical filter in the chamber, allowing only the 330 nanometer wavelength of light to pass, and this filtered light is measured by a photomultiplier tube. The photomultiplier tube contains a series of plates, the first being the photocathode. This plate emits electrons when struck by photons from the process. The dinodes each release electrons in greater numbers when struck by electrons from other plates. The anode is the plate in which the electrons exit the tube. Each of the plates is biased with a negative voltage by means of a voltage divider network referred to as a dinode chain. The source of the plate voltages is typically between -500 and -2000 volts DC. When a photon from the process strikes the photocathode, electrons are released from this plate. These liberated electrons strike the remaining series of plates in the tube in a cascading effect. An amplification of up to 1 million times is possible with the photomultiplier tube. An AC coupling capacitor provides us with an amplified electrical signal which is directly proportionate with the number of photons striking the photocathode. This voltage is the source of our measurement signal. There are a couple of ways to calibrate this process to zero gas condition. The first is to flow nitrogen into the measurement chamber and record the resulting signal voltage. A second way would be to turn the UV lamp off, no ultraviolet light, no fluorescence, no signal voltage. An independent light source is used as an optical test device. This is usually an LED or an incandescent lamp. When activated, this device simulates the light that would normally be produced by SO2 fluorescence. This is very useful in testing the PMT as well as any associated electronics. If an otherwise non-functional analyzer responds to the optic test device, then the problem must be pneumatic in nature. There are a couple of problems associated with this method of SO2 measurement. The first is that the process is pressure sensitive, so we'll need to monitor the pressure in the measurement chamber. Secondly, hydrocarbons in the form of unburned fuel are usually present in the sample, and these compounds fluoresce. A device known as a kicker is used to extract these compounds from the sample prior to delivery to the measurement chamber. Finally, nitric oxides also fluoresce. Although these compounds are typically in small concentrations in today's low-NOx industrial environments and are not usually a concern, they can be problematic at higher concentrations. One possible solution is to place a high-concentration NOx cell in the UV light path. This approach serves to absorb any UV wavelength that might cause NOx to fluoresce prior to entry into the measurement chamber. However, the preferred approach is to retune the process to measure light in the 360 nanometer wavelength. SO2 doesn't fluoresce as much at this wavelength, but NOx response is significantly less. The end result is that we sacrifice some SO2 signal strength for NOx rejection. Pulling on the upper corners will release the front panel. Flip it down and out of the way. Rotating the cam lock fasteners 90 degrees in either direction will unlock the top cover. The front panel is slid back and lifted off. All 9800 series analyzers are divided into two sections, the electronics tub and the sensor tub. The electronics tub is the same in each analyzer. The 12-volt power supply is a sealed unit and provides a single voltage to the analyzer. The voltage regulator board accepts 12 volts from the power supply and provides all the power needs of the analyzer. There are test points for each voltage provided. The microprocessor board is the computer that controls all the functions of the analyzer. All 9800 series analyzers use the same board, although the firmware may be different. The sample filter is a 5-micron Teflon disc that needs to be changed periodically. The flow block monitors sample flow through the analyzer and adjusts the pump speed as necessary. The sample pump utilizes an impeller with graphite vanes. When rotated, the impeller draws sample in through the inlet port and out the outlet port. This pump cannot be rebuilt. The valve manifold contains 3 solenoid valves and routes gases into the analyzer. The sample valve is energized during normal operation, and of the 3, is most likely to fail. The background valve routes zero air from the scrubber into the analyzer during a background, which is essentially a zero calibration. The span valve introduces gas from an external bottle into the analyzer for automatic span calibrations. The preprocessor board interfaces the microprocessor board with all the other components in the sensor tub. J5 is the test connector on this board. The kicker scrubber provides the clean air needed for kicker operation. The zero air scrubber provides SO2 free air to the analyzer for backgrounds. Both these scrubbers are filled with activated charcoal. The kicker is a tube within a tube device that removes any hydrocarbons present. These molecules migrate from the inner tube to the outer tube through osmotic action. The kicker has a finite lifespan. The optical bench is the heart of the analyzer and where all measurement occurs. A metal door on the UV lamp housing shields the user's eyes from the damaging effects of ultraviolet radiation. The UV lamp and lamp drive board are located inside. The reference detector is mounted inside the detector housing. The PMT housing contains the photomultiplier tube used to measure fluorescence. The base which the tube plugs into is actually an integrated preamp and high voltage power supply. The measurement chamber is pneumatically sealed and is where the fluorescence of SO2 actually takes place. The optic test lamp is used to simulate the light that would otherwise be present during SO2 fluorescence and is a very useful diagnostic device. It is mounted on a tube called the dump. The sample inlet is the steel fitting on top of the measurement chamber, and the outlet is the steel fitting on the dump. To remove the optical bench from the sensor tub, we must first remove the kicker. Take these fittings loose. If you loosen these fittings, you'll permanently damage the kicker. The kicker is held in place by 2 captive screws. Loosen these, remove the assembly, and set it aside in a safe place. Unplug these 4 electrical connectors. There are 4 captive screws securing the optical bench in place. Take these loose. We'll also need to disconnect the sample outlet tube from the flow block. Grab the metal bar that connects the PMT housing to the measurement chamber and lift the optical bench out of the sensor tub. To gain access to the inside of the measurement chamber, we'll need to remove these 5 screws. cleaning fluid and wipes must be of optical quality. Wipe out the interior of the measurement chamber as well as the sealing plate. Clean the optical filter and the UV plano-convex lens as well. Don't forget the O-ring before reassembly. To replace the UV lamp, unplug its connector and take the clamp screws completely loose. Flip the clamp down and remove the lamp. To replace the lamp drive board, unplug the power connector and pry the board loose at the corners using an Allen wrench. Reverse the lamp removal procedure for replacement. We'll talk about adjusting the lamp later in this section. To gain access to the detector assembly, remove the 2 screws from the housing cover. An Allen wrench is also handy here for prying the detector board loose from its retainers. To gain access to the PMT housing, we must first separate the halves of the optical bench. We'll need to remove the mounting plates from the PMT housing. Remove the two screws that mount the wiring pigtail to the PMT housing and disengage the internal connector. Remove the outer screws from the PMT housing cover and lift the cover off. There are two screws securing the PMT block to the cooling fins. Remove these. Carefully lift the PMT block from the assembly and remove the cooler spacer and thermoelectric cooler. Take great care when handling the TE cooler. It is of ceramic and metal construction and is very easily damaged. Remove the two screws holding the PMT preamp and high voltage power supply in place. Carefully slide the PMT from the block, firmly grip the base of the tube, and wiggle the preamp loose. The thermistor used to measure temperature is the only remaining component in the block. Remove its retaining screw and slide the thermistor from the block. A fresh coating of heatsink grease is applied to the thermistor once the old grease is cleaned off. Reassemble the block assembly once the old heatsink grease is cleaned off. A fresh coating of heatsink grease is applied to both sides of the TE cooler. Apply the grease evenly, but somewhat sparingly, or you'll make a mess. Place the PMT block on top of the cooler and reinstall the block retaining screws snugly. If you over-tighten these screws, you will crush and permanently damage the TE cooler. Reinstall the PMT housing cover and insert 2 new desiccant packs. The desiccant packs prevent condensation on the PMT, and it's not recommended you reuse the old ones. Reassemble the optical bench and reinstall it into the sensor tub. To adjust the UV lamp, we'll need to inspect the signal on the preprocessor board's test connector using an oscilloscope. The test connector is labeled J5 and is close to the front of the board at the top. A scope lead is attached to pin 3, labeled Ref X2, and the grounding lead is attached to TP1, labeled AGND. Remove the kicker, if installed, to provide better access to the UV lamp, and attach the scope leads. Loosen the UV lamp clamp screws to allow easy movement of the lamp. Lamp adjustment entails rotating the lamp and/or moving it from side to side to obtain the desired signal. Set the scope voltage selector to 0.5 volt per division and the time base selector to 20 milliseconds per division. While watching the scope, rotate the lamp to obtain the strongest signal possible. Next, move the lamp from side to side to again obtain the strongest signal possible. Repeat these 2 steps as necessary to obtain a 2 volt peak-to-peak signal. A signal less than 3/4 of a volt is unacceptable and the lamp should be replaced. With proper care and maintenance, your 9800 series analyzer will give you years of trouble-free operation.